So what happens in general for changes of variables in double integrals is that we can transform using a transformation t, a given transformation. I can transform my integral by writing what is the x coordinate in terms of the new variables u and v, the y coordinate in terms of the new variables u and v, but then I have to multiply by a correction factor. So this is what we call, what we've called before a correction factor, and it turns out that number has history, and it's called the Jacobian of the transformation. And it's a number that we're going to be able to calculate, and it's due to work of Carl Gustav Jacob Jacobi, who expressed, sort of developed the theory of how to do these transformations correctly and what is the correction factor every time. Okay? And the correction factor, when we change variables in double integrals, that Jacobian is given by either this formula, or I'd rather just remember this determinant. So it is given by a determinant that is taking derivatives of the transformation functions in x with respect to u, x with respect to v, in y with respect to u, and y with respect to v. So let's compute some Jacobians. Let's find the Jacobian of a polar change of coordinates and hope that the correct Jacobian in this case is r, which is what we've been using all along. So the Jacobian will be the derivative of x with respect to r, derivative of x with respect to theta, derivative of y with respect to r, derivative of y with respect to theta. I do have here are my x in terms of r and theta, and my y in terms of r and theta, and those are the functions I'm taking derivatives of. If x is not given in terms of r and theta, but r is given in terms of x and y, then first I have to find the inverse and really write my new coordinates in terms of r and theta, x in terms of r and theta, and that's what I'm going to be taking derivatives of. So what is the derivative of x with respect to r? It's cosine theta. What's the derivative of x with respect to theta? That will be minus r sine theta. We're doing partial derivatives like we learned before. The partial with respect to y, the partial of y with respect to r, that is sine theta. And the partial of y with respect to theta, that is r cosine theta. And remember how to do a 2 by 2 determinant. I multiply the diagonals is cosine theta times r cosine theta minus the product of the anti-diagonal. So sine theta times minus r sine theta. So that is going to be r cosine square theta plus r sine square theta. And there you go. This is going to be r sine square theta plus cosine square theta. And the sine square plus cosine square is 1, so this is r. So that is the conversion factor we needed for polar, according to Jacobi, is r, which is the correction factor we told you needed for polar coordinate change of variables. But this is where the general theory tells you it is r. All right? So let's do a few more. What is the change of variables that we did before? X is u divided by 2, y is v divided by 2. I hope that this Jacobian is a fourth, because that was the change of coordinates. A fourth seemed to be the one that worked if I was going to do the integrals as we did. So what is the Jacobian? In this case, the Jacobian will be the derivative of x with respect to u that is a half. The derivative of x with respect to v, there is no v in there, so it's 0. The derivative of y with respect to u is 0. The derivative with respect to v is a half. So this determinant is a half times a half minus 0 times 0. So it is 1/4, as we hoped. So that is the conversion factor you have to use in this change of variables. Okay? All right. So let's try this one. We also use this one. Remember that we used this change of variables, but the integral came out to be the same. So I'm hoping that the Jacobian in this case is exactly equal to 1. So let's see if that's true. I have to find the derivative of x with respect to u, but x is not solved with respect to u here. So either I can find the inverse function, so I have x in terms of u and v and y in terms of u and v, or we can use a fan favorite, which is implicit differentiation. Do you want to do a transformation or implicit differentiation? We haven't even touched implicit here, so let's just do again how to invert this transformation. So I want to solve for x and y in terms of u and v. So I already have y is already in terms of u and v, and then x will be u minus y, which is v, so it's u minus v. So the functions that I'm going to be using to take derivatives of are x is u minus v and y is v. Those are the ones I have to take derivatives of. So now I can figure out what is the Jacobian of this. And it's going to be the derivative of x with respect to u. What is the derivative with respect to u? 1. What is the derivative of x with respect to v? Minus 1. What is the derivative of y with respect to u? 0. And the derivative of y with respect to v is 1. So now take the determinant. This is 1 times 1 minus 1 times 0. That is 1 times 1 is 1 minus 0. That is just 1. Perfect. So the Jacobian explains why when we use that transformation, we actually didn't have to use any correction factor, and we got the right answer. Those are the nicest transformations are when the Jacobian is exactly 1. But sometimes you actually need those Jacobians to be able to complete the integral regardless. Let's figure out what is the Jacobian here. This is more complicated, and it's not just going to be a number. Sometimes it's a function itself. The Jacobian is a function because the transformation is really messing up the geometry of the region we're integrating over, right? In here, we saw that two regions, two of the sides, like these two sides that were at 90 degrees, now they are parallel. So this transformation is now really changing the geometry of the region, and just comparing areas of the two regions is not enough. You actually have to see how the area is being changed as you move along in the region. And that's what the Jacobian is computing for you. So here, x is a function of u and v. Y is a function of u and v. So I can just take the Jacobian directly. So let's see what the Jacobian is. The Jacobian is going to be the derivative of x with respect to u. That's 2u. The derivative of x with respect to v, that's minus 2v. The derivative of y with respect to u is 2v, and the derivative of y with respect to v is 2u. So in total, I get 4u squared plus 4v squared or 4 times u squared plus v squared. So that Jacobian is a function of u and v. Just like the Jacobian of for a circle for polar coordinates, it wasn't just a constant, but it was taken into account that a square region is transformed into a circular region and is doing something to make sure that the farthest we're from the origin, we are actually counting more area than if we're closer to the origin. Okay, so now we can do integrals and set up integrals using the Jacobian correctly. So let me first set up this integral in this region, and then we're going to transform it to this region. So in Cartesian coordinates, we already said that I would rather move in y first from 0 to 2 dy, and then from y squared over 4 minus 1 to y squared, what was it? It's here. It's going from this one to this one. So it's going to 1 minus y squared over 4 dx, and then the function that we're integrating is the function y. So now I'm going to transform this to u and v. The region is very easy, so I can just go, for example, from 0 to 1, 0 to 1 in any order. By Fubini, I'm going to be able to change the order if somehow that was convenient. The function y is 2uv, so I have to transform the function into u and v. And now I have to multiply by the Jacobian. In the Jacobian, we just found that is this function over here. So it's actually 4u squared plus v squared. And this is the correction factor. And now this is just polynomial. It's a polynomial function in u and v. So it's not that complicated to integrate. And that is, it gives me, is equal to 2. Okay? But you do not get 2 if you integrate without that correction factor. You would get some other number that is wrong. So the correction factor makes sure that if I'm going to do this, I do this, but taking into account how the transformation is changing the geometry of my region. No, the transformation, we would start with an integral that is over a region like this, and then, which is not something, it's not a skill where we're finding out how to do here in this class, but you would start with this and then find some transformation that brings it to some, hopefully a rectangular region, a parallelogram region, something that is easier to integrate over, that is going to make my integral easier to work with. This is not terrible. This is not a terrible integral to do, but this is much easier to do. So it is not always going to be from 0 to 1 to 0 to 1, but we're hoping to see this transformed into something that is a much simpler region. Let me give you an example to finish with of this integral. The integral is over a trapezoidal region with vertices. So what vertices are those? Let's draw those. 1, 0 is here. 2, 0 is here. 0 minus 2 is here. And 0 minus 2 is here. 0 minus 1 is there. So the region we're integrating over is this region. And I want to do some transformation that will allow me to compute this integral, which seems very complicated with that x plus y and x minus y on top. So what someone decided is to use the transformation that I'm going to do is u is x plus y and v is x minus y. So I end up with something that is just, at the end of the day, if I transform this function, it is going to be E of u over v, which I can integrate with respect to u, I can integrate with respect to v, hopefully. Okay? So that is the integral that I would like to do, and you have to figure out how to do this transformation correctly. So we would have to first figure out what are the new bounds, and also how to figure out maybe the transformation. How do we figure out what x is and y is in terms of u and v, so I can, in fact, use the Jacobian of this transformation, okay? So let me do both things. So if I try to solve this system in terms of x and y, the first thing I would do is write x, or write y, let's say, as u minus x, and then plug into the other one, and I get that v is x minus u minus x, and that gives me, let's see, v plus u is 2x, so x is u plus v divided by 2. Okay? And then what is y? Y is u minus x, x is u plus v divided by 2. So what I get is u divided by 2 minus v divided by 2, so u minus v divided by 2. So that is my transformation. And I can now find the Jacobian that I'm going to use once I actually try to set up the integral. I will need the Jacobian. So the derivative of x with respect to u will be a half. With respect to v is a half. With respect to u is a half. With respect to v is minus a half. So what I get for a Jacobian is minus a fourth, minus a fourth. So it is actually minus 2/4, so minus a half. So that's what the Jacobian is. Okay. So now I would have to also transform the region. And let me just tell you what the transformation is. I would do exactly the same thing I did before. Take this line and see where it goes. Take this line, see where it goes. And it turns out that the transformation brings this to some other trapezoid that is over here. Okay? So how would I integrate that trapezoid like that? I would go again in y and then go x from here to here. So you can set up that integral.